Let's see here. This is Romans chapter 12, verse 2. It says the following. It says, "And do not be conformed to this world, but be transformed by the renewing of your mind, so that you may prove what the will of God is, that which is good and acceptable and perfect." It's Romans 12, chapter 12, verse 2. I'll begin with a word of prayer. Heavenly Father, we thank you again for this opportunity we have just to meet together and study your creation. Just pray you'd give us understanding about determinants, and just pray that you be glorified in this day, Lord. In your name I pray, Lord Jesus. Amen. So let's see here. I think I've showed you most of the tricks. I mean, we could do some more examples, obviously. So let's do that. So probably should do an actual example of Cramer's rule, since we derived the rule, but we haven't actually put it into practice, right? So let's do one of those. I think Cramer's rule is especially nice for problems which have like a symbolic aspect to it. You know, if you've got some letters running around in your coefficient matrix, it really is not joyful to do Gaussian elimination on such a thing, because of course that would inevitably force you to start thinking about case-wise logic, like this is non-zero because I just divided by it and all that jazz. So it's super nice to just have a tool which allows us to solve some symbolic problems with just one foul swooping formula. All right, so like a plus, I don't know, 2y plus 3z, and then we've got, let's say, bx plus 3y minus z, and I've got cx minus y plus 2z equals to, let's see here, let me make it easy on us. Let's put 0, 1, and 0 here. That'll make our life relatively easy. Let's solve this system with Cramer's rule. All right? So my first order of business is to write down A. My augmented coefficient matrix, my coefficient matrix here would be what? A, 2, 3, B, 3, minus 1, C, minus 1, 2. That'd be my coefficient matrix, right? And then, so this guy right here, taken as a vector, gives me B as what? 0, 1, 0. That's my inhomogeneous term. And so from that, using the notation I use to derive Cramer's rule, A1 would be like 0, 1, 0, 2, 3, minus 1, 3, minus 1, 2. A2 would be ABC, 0, 1, 0, 3, minus 1, 2. And A3 would be ABC, 2, 3, minus 1, and finally 0, 1, 0. All right? Now Cramer's rule says what? Cramer's rule says you can solve this system by formulas. In particular, x is equal to the determinant of A1 divided by the determinant of A. Y is the determinant of A2 divided by the determinant of A. Z is equal to the determinant of A3 divided by the determinant of A. So what are those? You guys help me out. What's the determinant of A? You guys can make me calculate? Let's see here. I guess I'll do it down here. The determinant of A, I see A times 6 minus 1 minus b times 4 plus 3 plus c times minus 2 minus 9. I decided to expand on the first column. I don't know why, I just did. It'll give me a nice formula, I suppose. So what I got for the determinant of A is 5A minus 7B minus 11C. Now, if you got something else, I'd like to know. I don't really want to repeat the 1 equals 3 incident. Okay, so I guess there's agreement by silence. Take it. So guess what? We've already, so my son Matthew is 10. Today the answer to some math question, or yesterday, the answer was 34 over 7. And he said that he didn't like that answer because it wasn't a real number. That was like a fake number. It wasn't done. See, because to him, unless you find the decimal form of it, it's like, yeah, okay, it's 34 divided by 7, but what is it? It's like, no, it's 34 divided by 7. So he's rejecting this as a concept. My 10-year-old does not believe in rational numbers. Oh well. Thought I raised him right. Maybe he's an engineer. Oh man. No, it's okay. It's okay. It's okay. I guess it's okay. It's okay. They can be whatever they want, just not an English major. All right, so determinant of A1. I would suggest that we expand around this guy. Plus, minus, so I've got minus the determinant of 2, 2 on the diagonals, and minus 1 and 3 over there. The determinant of A2, I suggest we expand along this entry right here, right? I would expand on the second column, plus, minus, so it's a plus. And we need the determinant of everything else that were not in the second row and second column, namely A, 2, and the C and the 3 here. The determinant of A3. All right, so I'm going to expand on this one here for my Laplace expansion on the third column. Plus, minus, minus. So minus the determinant of, let's see, A2, C minus 1. All right, what do those work out to? What we got here? We've got ourselves a 4 plus 3, which gives minus 7 for the first one, 2A, minus 3C, A plus 2C, I believe. So there you go. Minus 7 goes here. 2A minus 3C goes there. And A plus 2C goes right here. And there you go. That's the solution to this 3 by 3. And when can it be solved? Right, which is tantamount to saying that what is non-zero? Yeah, the determinant of the coefficient matrix, right? That's the condition needed for the inverse to exist. So, and Kramer's rule gives you the unique solution. Oh. Now, for a non-symbolic problem, I think this is absolutely the wrong way to go, right? Like, if I don't have variables in the coefficient matrix or something, it's probably better to not do this, right? What do you guys think? I mean, determinants are not that easy. And this was particularly nice because I purposefully chose for us a super nice non-homogeneous term here, which made many of the subdeterminants trivial, right? Because usually this calculation here is like 60%, 66% bigger, right? Because there's the other two subdeterminants to think about. So like how many terms are there in a determinant, by the way? Can you tell me what the determinant is if you just think in terms of like raw combinatorics? It's formed by taking a matrix, right? And taking the product of n distinct entries in the matrix, right? How many ways are there to choose n distinct, lists from n squared elements? The answer is n factorial. There are n factorial distinct, ways to arrange the entries in a matrix to make a product. So every time you calculate a determinant, you're looking at something like n factorial products added together or subtracted together because it's got a plus minusness to it, right? It's nasty, right? So like, for 3 by 3, we're talking about 6 factorial, we're talking about 6 terms. For a 4 by 4, we're talking about 4 factorial, that's 24 terms. For a 5 by 5 matrix, we're talking about 5 factorial, that's 120 terms for the determinant. For a 6 by 6 matrix, we're talking about 6 factorial, that's 720. For a 7 by 7, we're talking about 5040. I mean, there's a stupid number of terms in the determinant. And so like, it's just much easier to do row reduction if you can, right? And I think for something like a 7 by 7, I'd probably still do row reduction despite the case-wise analysis, just because the determinant gets so unwieldy for larger sizes. Okay, so there's that example I thought would be helpful to you. Let's see here, what else should I show you? There are some formulas we can build by the determinant, which I'll get the projector out for that. But the other thing I wanted to write up on the board is, so we have a couple different things I've played around a little bit with. Definition, ON, ON is equal to A in Rn by n, such that A transpose A is equal to the identity, all right? Now, I don't expect you to memorize these. If I inadvertently put this on a test and I forgot to define it, you could ask me and I'll tell you what it is, okay? So I would typically include this. So these, we've had some homework problems about these. This is the set of orthogonal matrices. Orthogonal matrices. There's also something called SON. These are the special orthogonal matrices. So here what you have is A and ON such that the determinant of A is equal to 1. See, so notice what's the deal for orthogonal matrices? If you've got, think about this, if you got A transpose A equal to the identity, and we take the determinant of that, what happens? We've got the determinant of A transpose A equals to the determinant of I. All right? So we do a product of the determinant. The determinant of the product is a product of the determinants, right? So this gives me the determinant of A transpose times the determinant of A is equal to 1, because the determinant of I is 1, right? But what was one of the properties of the determinant? The determinant of the transpose is? It's equal. So this is literally the determinant of A squared. Right? Something I should mention, like almost every engineering book and stuff refuses to write determinant of A because it's just so much trouble, and they write this instead. I just never use this notation because it's too close to like the bracket notation for matrix for me. Yeah.
Is that supposed to be inverse of the transpose?
No, I mean, it is true. You're not wrong that A transpose is equal to A inverse for that's an alternate way of characterizing a orthogonal matrix, but I'm just taking, what I want to show you is that if you have A transpose A equals I, that forces the determinant of A squared to be equal to 1, right? And so then what? That means the determinant of A is what? Plus or minus 1, right? By the square root property. So what that means is that if you look at ON, it's actually equal to SON unioned with what? With the matrices that are orthogonal and yet have determinant what? Not 1, but -1. These are the two components of the orthogonal group. Orthogonal matrices, when we study them, they're the ones that have this like neat property that an orthogonal matrix times a vector, dot product with another orthogonal matrix times a vector, just gives you the dot product again. So like orthogonal matrices, in this sense, preserve the dot product, which means that if you look at the transformation, right? We haven't talked about transformations much in here yet, but a transformation is just another word for mapping. So like the transformation I'm talking about is x maps to ax. That's an example of a transformation, right? It's transforming space. It turns out that that kind of transformation, if it's done by an orthogonal matrix, will preserve the distance between points and the angle between vectors, which is kind of neat. And but the thing is, with an orthogonal transformation, you can also have determinant -1. And to get a sense of what determinant -1 can do, it can do something like this. Oops, no, that was determinant 1. Oh, there we go. See that? It turned it inside out. That's what determinant -1 can do. It can rip stuff inside and put it out. So determinant -1, it's not a physical motion in that sense, right? Rigid motions, motions that keep things rigid. Ah, come on, there we go. Determinant 1 is a rigid motion. Determinant -1, things like inversion, reflection. Anyway, so there's that. All right, so you guys got any questions while I'm getting my projector out here? We do have some time for some questions today. Wait a minute, it's already out. Wait a minute, top hat. Almost forgot about top hat. Okay, that's not true. I didn't forget about it at all, if you know my meaning. Some friends you forget about, some friends you ghost. I've heard. Let's see here. Where's that thing? So the determinant is super useful if you ever want a formula that's, determinant is just super useful, period. But it's also very useful for creating formulas for things. And I have a few of these in my notes. I'll show you. So apparently 2117. Exciting, yes? All right. So just to talk about some of these things, and you guys can jump in and ask questions about your homework as you think of them. So here I have Kramer's rule. And so we went through this derivation the other day. And I think I said something like sort of almost a sort of idle threat about you deriving the formula for the inverse on the test. Like, that's not reasonable in the sense that there's that technical nastiness that we got stuck on in class. So that's why I wouldn't ask that particular one as a test question. I somehow, when I was preparing for class, it escaped my notice. So that's the kind of thing I might make 321 students do, but you guys, it's a little bit much. There's a particular quirk to the calculation that I just think makes it not a 221 question. Anyway, now using it, that's a different thing. But so there's, here's a plain Jane example of Kramer's rule for a 2x2 system. I personally wouldn't use Kramer's rule for a non-symbolic numerical 2x2 system. Like, I think it's the wrong tool. On the other hand, if you guys take advanced calculus with me, for example, you can start looking at questions like, suppose you've got these two nonlinear equations. Well, wait a minute, one of these is quite linear. X plus y plus z plus w equals to 3, right? That's a hypervolume in 4 dimensions, is what that is. And then you've got this x squared minus 2xyz plus w cubed equals to 5. Well, I don't know what that is, but it's not linear. And but if you think about that, you've got a 4-dimensional context, x, y, z, w. Yeah, 4-dimensional context, and you got two equations, right? So that means you're looking at some kind of surface in 4 dimensions. And if you want to understand, is it possible to write two of the variables as functions of the other two variables, it turns out what you can do is solve for the differential. You can solve, first of all, take the differential of the equations, which you already learned how to do in Calc 3. Just straight up take the differential. Sorry. And then you can solve for the differentials of your potential dependent variables. So like, if I solve for dz and dw, that will tell me what the conditions necessary are to think of z and w as dependent variables on the remaining two variables x and y. And how do you solve for differentials? See this differential equation, it's linear in the dx, dy, dz, dw. It's just that the coefficients are variable. So I can rearrange it like this, and you see I've got a system of equations in dw, dz, like so, and I can look at it, well, I've got this coefficient matrix times d. So actually think of the differentials as variables in the linear sense. And once I have this, well, this just yells at me Cramer's rule, because the coefficient matrix is variable, is like symbolic. Cramer's rule is like the right way to solve this kind of like symbolic linear problem for sure. And so I do that, and lo and behold, I get dz is equal to this monstrosity, right? Which works out to that. And then the cool thing is, once you have that done, you can read from this the partial derivative of z with respect to x, holding y fixed, which makes this go 0, which gives us that. Or the partial derivative of z with respect to y, holding x fixed, which would make this go to 0. X is fixed means this little sub x here tells you that your independent variables are y and x. So when you're taking a partial derivative with respect to x, you make y fixed. When you're taking a partial derivative of y with respect to x, you make x fixed. This kind of differentiation is necessary, for example, for thermodynamics. When you're calculating partial derivatives in thermodynamics, you have a set of state variables. You might have like 12 state variables, but you're only going to take, well, you might have like 4 state variables in a problem. You're going to take 2 of those state variables and write them as functions of the other 2. And then you probably got like a pair of constitutive equations of state, which bind the variables together in the same way that these 2 equations did. So this kind of calculus comes up in thermodynamics. In fact, it's really where I learned this kind of calculus was thermodynamics. This topic in particular, Stewart is very poor on. You can't read about constrained partial differentiation in Stewart. It's just not there. And then, so the other problem I should mention is like the variation of parameters in differential equations. We form the particular solution as a linear combination of the fundamental solution set, and the v1 through vn are parameters which we don't know, functions, and you differentiate that thing and again and again and again and again, and you impose this set of conditions. So it's kind of like if you're looking for a wife or a husband, you have a set of conditions you can impose, right? Like doesn't like Star Wars, doesn't like Marvel, likes Lord of the Rings, enjoys chess, not checkers. And you can add this list, right? And then you can see if that is like, has brown hair, not blonde hair, whatever, on down the list. And then you can try to, solve that set of constraints. Now, maybe you add too many constraints, so there's no solution, right? You gotta be careful with that. But if you happen to get a linear set of constraints, then you can solve it uniquely, and that solution is, of course, known as the one. So, although I personally don't believe in the one, or the cult of the one, if you know what I'm talking about. But anyway, so these conditions are posited as this, and it turns out that these conditions are solvable because when you study differential equations, this coefficient matrix has a non-zero determinant because the solution set to the homogeneous problem is independent and independent solutions. Anyway, so long story short, Cramer's rule applied to that gives you the variation of parameters formulas, and here they are. So like n equals 1, Cramer's rule, and this derivation reduces to the, I think the integrating factor method. N equals 2, this is the most familiar one. Cramer's rule on this matrix, you swap out the inhomogeneous term, which is 0 f over a naught for that one here, and that gives you this, and you swap it out over there, that gives you that. You divide by the determinant of the coefficient matrix, which is called the Wronskian of the fundamental solution set, and out pops. These are the formulas for variation of parameters that we teach you guys in Math 334. But it's Cramer's rule that derives them. And then there's also variation of parameters for more things. No one cares about this. You guys can look at this in differential equations. We don't care about it here. But here's a hideous variation of parameters third order problem, which I don't teach this in differential equations because it's just too horrible. So I'm certainly not going to like force you guys to do it here. But there is variation of parameters for like higher order systems in terms of Cramer's rule set up for like higher systems. And in fact, this can be derived for an nth order problem. So anyway, in fact, this works for not just calculus over over the reals. The derivation I just showed you equally well applies if you do calculus, say, over a finite dimensional real associative algebra. I worked that out with a student a few years ago. Anyway, so getting back to determinants, this here is a super cool formula. In quantum mechanics, you might have a bunch of wave functions, chi1 through chi n. All right, so a wave function is something you study in quantum mechanics, and it's for these, it's just a function of position. Now, so this is for a system of fermions. Now, fermions have this property that you can't have two fermions in the same physical space. All right, so well, with the same set of quantum numbers anyway. In contrast, bosons can kind of occupy the same physical space. Like, for example, you get two you get two flashlights, right? And you like cross the beams. It's not like you're feeling like like it's hard because the light's bumping into the light, right? I mean, like because light just kind of goes through each other. It's like that. Electrons, on the other hand, they, like everything we're feeling is essentially electrons bumping up against electrons, right? So to make it turns out for the reasons of quantum mechanics, you want it to be such that if R1 is equal to R2, this is 0, because you want to say that the probability a fermion can be, two fermions can be in the same position, that R1 could be equal to R2 should be 0. To make that happen, you can just put this formula here. So like anytime you have R1 equals to R2, that would make the two rows equal, which would make the determinant 0. So you can use determinant in quantum mechanics to create this wave function for a composite system of fermions, like if you wanted to. This will not be on the test, obviously. This one, on the other hand, is a nice test question. So here we have the so-called van der Monde determinant. And check this out. So what you do is you put 1, 1, 1 here, x1, y1, x2, y2, xy. Let's just think about this for a second. What happens if you put x equals to x1 or y equals to x equals to x1 and y equals to y1? What happens to the formula? We don't need to write things out for this. We should just talk about it, think about it. What happens when I put x equal to x1 and y equal to y1 here? What happens? The first row and the third row are equal. Therefore, it's 0, right? Now, does that mean so? That happens. So what I'm trying to say is that x equals to x1 and y equals to y1 is in the solution set to this equation. What kind of equation are we looking at? Well, think about it. You've got x here, you've got y here. Could this be quadratic? What kind of equation is it? If you think about multiplying it out in your mind's eye, you should see that it's actually just going to be linear in x and y. If you've got a linear equation in x and y, what are you looking at? The equation of a line, right? ax plus by equals to c. That's the general equation of a line in 2 dimensions. And you can, through properties of the determinant, easily see that x1, y1, and x2, y2 are in the solution set. Therefore, this must be the 2-point formula for the line. because this is the line that goes through x1, y1, and x2, y2. It has to be the two-point formula for the line in disguise, and that's what I derive. See, if I do, so what do? I just do like R1 minus, this is my old notation. Look at this clunky notation. This is a very old example. See, because I later have replaced this with just what? I would just write arrow R2 minus R1 with the intention that R2 is modified, right? And R3 minus R1 with the intention that row 3 is modified. But here I'm explicitly writing goes to R2, goes to R3. So we get that. And then what? Let's see here. And all right. Whoa, that's a weird calculation. Oh, I'm an idiot. So my point was that we just did 2 row operations, right? So actually, I'm not convinced. I didn't want to think about what K1 and K2 are here, but I think the determinant of those kind of row operations, isn't those kind of row operations the ones that we had in the LU decomposition? And aren't those exactly the like lower triangular matrices? So this way I'm doing this calculation here is needlessly complicated. Like, you know that K1 and K2 are actually 1. Because we're just doing row operations there. But anyway, it doesn't, my point was I don't have to think about it. I know that the determinant of an elementary matrix is some number, because elementary matrices are invertible, therefore they have non-zero determinant. So there's some K1 and K2 which corresponds to those the determinant of those row operations. And so I get that formula. And of course, once you get to here, you can see that the determinant is just, like the product of the differences of x2 minus x1 and y minus y1, and likewise x minus x1 and y2 minus y1. That's all equal to 0, so we divide by the K1, K2 and solve for y, and what do you know? It's the 2-point formula for the line, right? But if you understand this trick, you could easily write down a 3-point formula for a plane. What would it be? If this is the 2-point formula for a line, what's the 3-point formula for a plane in terms of determinants? So I'll start you out. 1, 1, 1, 1, right? Let me go back to the... So you said 1 what? X1, Y1, Z1. Yeah, and then what? X2, Y2, Z2, X3, Y3, Z3, and your variables, yeah, X, Y, Z. So if you ever want to create something that is 0 when like you can make the formula be 0 when, you can design a formula by just knowing that the determinant's 0 when the rows match up. This is a pretty cool trick for a formula building. That is the 3-point equation for the plane. That we never, do you remember from Calc 3 when I taught you guys the 3-point equation for a plane? Do not shake your head to this. That's a trick question. We never did such a thing. No, I mean, there is no such formula. Maybe it's some exercise in Stewart or something, but no, it's so hideous to actually write this down as like an arbitrary formula, you just wouldn't even attempt it. Of course, the 2-point formula for a line we teach to middle schoolers, I hope. At least high schoolers, right? We haven't stopped teaching that yet, have we? I hope not. But you could solve this thing for z, and you'd get the 3-point formula for the line, for the plane that contains the points, these 3 points. Unless what? What if these 3 points are collinear? Then I don't think it's helpful. You know what I mean? But then again, if the 3 points are collinear, that doesn't uniquely define a plane either. You know? What's the plane? So think of the 3 points as being this marker cap, and that marker cap. Which plane contains those 3 points?
A lot.
A lot, right? Any plane like this, or like that. Anything that, you guys know what I'm talking about. Here, any of these planes, right? They all got that line in it. Are you guys got questions about homework? I mean, I do have time for your questions. Yep. Oh, let me get it out. We're mission. What is it?
4.
4. Okay. So the last problem on the test, right? If you look at it, I think it's relevant to one of the problems on this mission, right? So let's see here. Where is that one? Like this one, problem 51. See problem 51 there? I would point out that if you look at the solution to the last test, the last problem, the bonus, actually has essentially what you need there, the idea. Like to calculate the trace, if you've got if Q is equal to P inverse RP, then I can use the trace of AB as trace of BA identity, and think of this as P inverse R as A and P as B, so I can commute those inside the trace. And when I do that, I get PP inverse, which is the identity, which gives me R. So this is an identity which says that the trace of 2 similar matrices is equal. And a similar calculation is possible for the determinant of similar matrices, right? You can use that determinant of the product as a product of the determinants to simplify that. What was your question?
I was about to ask about this one.
Oh, really?
Yes.
Oh, wow. Huh. What do you know? Well, that's cool. Does that help? I mean, I hope that helps. Where was I? The other one. Which one?
60 or 59.
60 or 59.
Or both.
By the way, problem 58, this is not hard. Like, what I did in example 2 is almost a solution to this problem, right? All you need to do is take the determinant of the defining equation and see what happens. All right? The fact that J is invertible shows you the determinant of J is non-zero. So 59? Oh, this one. So that is actually the Calc 3 formula for the determinant, written in a mathematically rigorous notation. Let me calculate one of those things in a style which will make the calculation of the next problem tractable. So let's just work out the A dot TAB equals 0 thing. I'll try it anyway. So A dot T of AB. All right, so that is going to be what we got here. A dot, and that's what the sum I equals 1 to 3. What we got there? Determinant of, how's it go? I need glasses. AB, EJ, and yeah, end of bracket, and then EJ out there. All right, cool. So first of all, what are properties of the dot product? the dot product distributes across sums, right? It distributes across addition, and you can pull scalars out. So by properties of the dot product, I can rewrite this as the sum, I equals 1 to 3, of the determinant of A, B, Ej. I've done nothing there, it's just a number. And let's move actually to what's interesting, A dot Ej. What is A dot Ej, though? So we're in 3 dimensions here, right? So A is literally A1, A2, A3, right? So A dot Ej for us is just A sub j. All right? So this is A sub j. It's the jth component of A. But then I can, by the properties of the determinant's multilinear, right? So that's the determinant of A, B, A sub j, Ej. What I use there is the multilinearity of the determinant with respect to the third column. Remember, we can pull numbers out of columns of the determinant, right? But we can also bring the summation inside the determinant. That's a property of the multilinearity with respect to the third column. What's that, though? What is the sum over j of A sub j, E sub j equal to? That's just A. Very good. I'm so happy you said that. So then what? Why is that 0? Right, because that's equal to minus the determinant of ABA. Flip it, like if we swap the first and the third columns, we get minus what we started with. Anyway, at this point, you don't even need to do that. Like, this is not a necessary step. My point is this is like 0. All right, once we get repeated column property we already have, determinant 0. And if you can do it for A, you can do it for B, right? Almost the same calculation will work for B. If you look at the next problem, come on, come back to me. Here I share with you the triple cross product for 4 dimensions. If you have 3 vectors and you take their triple cross product, if you will, you can create a 4th vector, which is perpendicular to the first 3. And if you could understand the calculation I just did, you probably could generalize it to this problem. Is there more? I guess what's interesting, the thing I didn't ask you, but it's actually really interesting, is that if you know that the length of the vector A is equal to the length of the vector B is equal to the length of the vector C for A, B, C, and R4, it turns out that the length of this thing I'm just defining there is also equal to, I'm missing an important thing here. Equal to what? 1. then that's also equal to 1. For what it's worth. So it's like that. And there's a way of visualizing this in terms of projections onto hyperplanes, but anyway, that's from another time and another course. So let me not talk about that here. Other questions about the homework? So like this one, any ideas, strategies? Lots of zeros, right? First column?
do it once in the third column first.
All right, so the answer is 1 times 3 times 2 times 1 times 7 times 1. So the answer is 42. How do I know that? No. I flipped, that's another way, but what I did was I flipped 3 and 4, rows 3 and 4, and I flipped rows, how many do I got? 6 and 5 and 6? Yeah, so if we flip rows 3 and 4 and we flip rows 5 and 6, it's diagonal. Each one of those flips costs me a minus, but minus minus is a plus. And then, of course, the answer is 42 because I made this problem. Last semester, I had a final, which worked out to 42 on like 5 questions. The final question was, how old do you think my wife is? It's called high risk, high reward. It also works for comedy. Some of the students answered correctly. Some of the students answered politely. But anyway.
What's the answer then?
Oh, I can't say. I just pose the questions. I don't answer them. But of course, you could expand, and you probably could do row operations. Like, there's lots of different ways to do this one correctly, but I'm just saying, look for that. If there's a lot of zeros, it may be that I have made it so it's nearly triangular, and just with a flip of a row or a column. Because once it's triangular, you just multiply by the diagonals. That is just faster than everything else altogether, right? So next time, we begin our discussion of coordinates, non-standard coordinates for Euclidean space. I think you'll find this material interesting and also challenging, what we're about to do. So anyway, thanks guys.